This is Dr. Hawkins again, and today I want to talk about rectifiers, which is one of the primary uses of diodes. We'll get into specialty types of diodes and diode uses a little later, but the basic rectifier, and that's the original purpose of the diode, was to convert AC into DC. If I feed an AC waveform into this diode, during the positive half cycle of the AC waveform, the diode's going to forward bias. It's going to give me an output that looks like this, where the peak voltage here, let's just call this VP, and this is VP out. VP out is going to equal VP minus the diode voltage drop 7/10 of a volt. It will take 7/10. It uses up 7/10 of that voltage in forward bias in the diode. Now we can also do negative if we want to. We just reverse the diode in the other direction. Well, before I get to that, I didn't finish this thought. During the negative half cycle of this diode, I don't get anything out. The diode's reverse biased. And the next positive half cycle comes along, and so on. And then we can do the same thing if we wanted negative voltage. We just reverse the diode. And what we get out in this case, during the positive half cycle, we reverse bias, so we don't get anything out. But during the negative half cycle, we get a pulse, and so on. Now, a more complete circuit, let's see, this is what we call a half-wave rectifier. We're using a transformer. Well, first of all, let's look at the supply voltage. I'm showing 170 volts peak. That's the same thing as 120 volts RMS. $60 hertz, so that's your standard house current. But it's 170 volts peak because we're going to want to deal with peak voltages over here on the right side. Now remember the transformer equation. If this is V1 going into the transformer and V2 plus and minus V1 and V2, and this 6:1 is called the turns ratio. Now, in this case, it's 6:1. Now, that does not mean that there's 6 turns on the primary and 1 turn on the secondary. It might be 600 and 100, or 6,000 and 1,000. You'll have a bunch of turns to get a good magnetic coupling between the primary and secondary coils. But the ratio is what's important here in terms of the voltages. So we'll assume those are large numbers of turns, but that reduces down to a 6:1 ratio. So that the transformer equation tells me that V2 coming out of the transformer, the secondary voltage we call it, equals N2 over N1 V1. These are AC voltages, so I tend to use lowercase letters for them. All right, so that says V2 coming out of the transformer. Now, if I use a peak voltage for V1, I'll get a peak voltage for V2. If I use an RMS voltage for V1, I'll get an RMS voltage for V2. But I want peak voltages here in this case. So my turns ratio in this instance is 1/6 of 170 volts. And that comes out to about 28 volts, I believe. I did something. Let's try that again. 170 divided by 6. Yeah, 28.3 volts. And again, that's a peak voltage. I put a peak voltage into the formula. I got a peak voltage out. Now we're going through a diode, and the diode is positioned so that I will get a positive pulse out during the positive half cycle and nothing out during the negative half cycle. And this is what we call just peak voltage going into the diode on the previous page. So my peak voltage coming out of the diode we could also call it the load voltage, your P-peak at the load, because that's coming out of the diode going to the load resistance. And I just picked an arbitrary number, 1K on them. That's going to be that peak voltage minus 0.7 volts. It's supposed to be a decimal point. I have trouble with decimal points using the stylus on the computer screen. So that's 28.3. And that'll leave me 27.4 volts peak. Now that voltage is going to look like this. Which doesn't look a whole lot DC like DC. DC is a flat line, remember? So to get closer to DC, one trick we can do is to add a capacitor in parallel with the load resistor. During the upswing of this voltage, the capacitor is going to charge, and when the peak voltage or when the voltage coming out of the diode starts to decrease, the capacitor tries to hold it up. If it don't make it, it's going to tail off, and that's usually more of a straight line. At an angle now, it's not straight across, it is decreasing. So that's closer to a DC. What you would see on the oscilloscope might look like this. Smaller eraser. Something like that. Where that is a DC value, the peak voltage roughly, but we have something here, the change in voltage we call the peak-to-peak ripple. And you can calculate that. I'm running out of room on this page, but I would like to put all this on the same page, so I'm going to put that right here. That's going to be my output peak voltage divided by the frequency, the load resistor, and the capacitor. Now, there's several different ways we can make that better. One is just the bigger we make the capacitor, the smaller the ripple voltage is going to get. So using a bigger capacitor or a bigger load resistor, either one would decrease that ripple voltage. But on the other hand, we're wasting half of our voltage here. We're just chopping off the negative half cycle and throwing it away. What if we could flip it over and use it to fill in those gaps and have more pulses closer together? It turns out there's a couple of ways we can do that. This one we're looking at here is called a half wave. Rectifier. The next one I want to look at is a full wave because it uses the whole wave. It flips, like we're just talking about, it flips the negative half over and fills in those gaps. So we call it a full wave, and we're going to use a center tap transformer. This is an abbreviation for transformer, XFMY. The way you make a center tap transformer is you wind the primary winding, and then on secondary winding, you wind half of it, and then you bring a tap out or a wire to the outside that you can connect to, and then continue on with the other half of the winding. Now, this is still a 6-to-1 transformer. What it's saying is if I have 12, let me get my pointer out here for a minute. If I have 12 turns here, one turn on the bottom half and one turn on the top half, if we didn't connect the center tap to anything, then that would be a 12-to-2, which is the same thing as a 6-to-1 transformer. So I'm still going to get 28.3 volts out over the whole secondary. So let me just draw that over here. This is my secondary. I'm still going to have but the center tap cuts that voltage in half. It's like we had a circuit that looks like this. Where each of these voltage applies represents half of that secondary coil. So it splits the voltage in half. But notice the polarities. If I put in a positive, well, I'll put in a sine wave. On this side, I'm going to get a smaller sine wave, but the same polarity. Down here, I'm going to get the same size sine wave as I had on top, but the opposite polarity. So when this one's positive, this one's negative, this one's negative, that one's positive. Now notice that each one feeds into a diode. So coming out of the top diode, I'm going to have this. Everywhere there's a positive half cycle, I get a positive pulse out. Down here, every time I have a negative half cycle on the input, I get a positive half cycle going into the diode. So I get a positive half cycle there and there. And then I tie those together. Those should all be the same level. I get a full wave rectified signal, but with half the voltage. My peak voltage now, instead of the 27 something volts, it's going to be the 14.2 minus one diode, because only one diode's active at the time. So I've lost half my peak voltage here. Now I can get it back if I wanted to. Instead of making this a 6-to-1 or a 12-1-1 transformer, I could make it a 6-1-1 transformer, which means a 3-to-1, and that gets me back up to my 28 volts. So all I got to do is change the windings or change out the transformer with 1.5 the windings. And then finally, we got the peak-to-peak ripple. We can add the capacitor. And again, we'll get the ripple voltage. It's supposed to be going down. Every time. So that ripple now is almost the same as the previous example. The peak output voltage coming out of the diode, still divided by the frequency, the resistor, and the capacitor. But we're only giving it half the time to die off in between pulses, so that cuts in half by a factor of 2. Now there is another way to do this, something we call a full wave bridge. Let's see, where did I hide that one? There we go. Whenever we have 4 components in a diamond shape like this, we call it a bridge. You can have 4 resistors in a diamond shape, have a resistor bridge, or you can have 4 capacitors in a diamond shape. It would be a capacitance bridge. Here we got 4 diodes in a diamond shape. We call that a diode bridge. And you can buy that already put together in one package. It'll have 4 leads coming out that each connect to one of the 4 corners. And we're back to our full 6-to-1 transformer now. And the 2 ends of the transformer feed into the top and bottom of the bridge. You notice we've got a ground and then the output to the load. Now, once again, coming out of the transformer, we have a full sine wave. Going into that diode bridge. And it's kind of like it has its opposite down here too, similar to the center tap one we had before. It's not grounded. It's two ends of the same thing. You can kind of think of it that way. So what's going to happen during the positive half cycle of the input wave, and that's this one, diodes 3 and 4 are reverse biased. And just leaves diodes 1 and 2 in the circuit that will be forward biased. That's going to give me, and the reverse bias 3 and 4 diodes act like open circuits. That's going to give me an equivalent circuit that looks like this. So again, I've got a complete circuit there because the grounds connect. The grounds connect to each other. So that is a completed circuit. And that's going to give me a positive pulse going to the top of the resistor. This is during the positive half cycle. Now, let's look at the negative half cycle. I want to bring another full bridge out here. During the negative half cycle, just the opposite happens. There's my negative half cycle. Now, during the negative half cycle, you get the positive pulse down at the bottom and a negative at the top. Here we had plus at the top and negative at the bottom. So this time, diodes 1 and 2 reverse bias, and they're open circuits. Diodes 3 and 4 forward bias. And we end up with an equivalent circuit. Let's see where I hid that. The bridge negative here. So once again, over here we had the plus on this side coming out of the transformer. Let's see, where did I put it? We have the plus on this side coming out of the transformer. Here we got the plus down here. This is plus minus this way. And once again, we have a completed circuit path where I get a positive pulse to the top of the resistor. And this is the same type of resistor I'm showing here and here and here. So once again, when we combine those together, we get a full wave. And this time we didn't cut our voltage in half to get there. Now once again, we can add the capacitor. And that's going to give us some sort of a ripple voltage. And here again, the ripple voltage is the same as it was in the previous page with the center tap. It's going to be the peak output voltage over 2 F RL FRLC, where this time DPO is going to be the peak voltage coming out of the transformer minus 2 diodes, or 1.4 volts. because no matter which one of those circuits is active, whether it's a positive half cycle or a negative half cycle, only two diodes are turned on at a time, but you do have to account for both of them. So you would have both diode drops you have to deal with there. Now I want to go ahead and talk about specialty diodes, but in order to keep my length of my podcast from getting too long and taking way too long to download, I'm going to stop this one right here, and I'm going to start a new podcast to talk about the specialty diodes. So watch for both of these to come out together.